Good afternoon, everyone, and thank you for attending our Defining Stack-Ups for Flex and Rigid Flex Circuit Boards webinar. My name is Ryan Wood, Content Marketing Manager here at Epic. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them in the questions panel, which is located in the webinar control panel, and we'll try to get to all of them at the end of the presentation. If we don't have time to go through all of your questions, we'll be sure to reply to you by email. Also, we'll be recording this webinar and posting both the recording and the slides on our website and YouTube channel. Our presenter today is Zachary Walker, our product manager of Flex and Rigid Flex circuits. His main responsibility involves interacting with customers' Flex and Rigid Flex products from start to finish. He assists in their product creation to ensure they can suit the customer's needs while still being manufacturable. He addresses concerns or issues that may arise during any part of the process. And he also oversees the quoting process for Flex and Rigid Flex PCBs. Zachary came to Epic with years of experience in the production and planning side of circuit boards. He's familiar with aspects of production involving engineering and manufacturing. And he has a bachelor's degree in chemical engineering from Texas Tech University with minors in chemistry, mathematics, and polymers and materials science. So without further ado, I will pass it on over to Zachary.
Thank you, and good afternoon, everyone. As he said, we're going to be discussing defining stack-ups for Flex and Rigid Flex circuit boards. So just to start from the beginning, we're going to go and do an overview of all the different stack-ups involving the materials used in the stack-ups and what part each material plays in the stack-up, alongside covering which materials would be considered standard and non-standard by our definitions. After that, we'll be doing examples of stack-ups, starting with Flex stack-ups, addressing things such as when too many layers becomes an issue and when it no longer becomes a Flex, alongside covering the bin radii for Flex. After that, we'll be following up with Rigid Flex stack-ups, where we'll be covering the Flex to Rigid transition zones. Following that, we'll be considering specialized constructions, starting with what we can do, things like air gaps, asymmetric constructions, diff connectors, and blind and buried vias. After that, we'll be following up with what might be outside of our purview, or what in some aspects of the industry might be considered advanced stack-ups, such as bookbinding or different rigid section thicknesses. And then finally, we'll be closing out with how your stack-up might affect the overall cost of a part and what can influence it to either increase in price or decrease in price. Starting with our introduction, why is defining a stack-up important? And in many ways, a stack-up will define all of the requirements of a design. It, at a glance, can tell you sometimes what the purpose of a design can be. If, for instance, it had shielding, if it indicates that signal integrity is a main concern, or if stiffeners are present, it might indicate that there's component areas or ZIF connectors, or even just mounting points within an assembly. Unfortunately, stack-ups as defined sometimes can either help or hinder a design based on how they're defined and how they're shown to us. So starting with the overview of stack-ups. So stack-ups are shown in a cross-section format where it's a shrunk down two-dimensional representation of the entire board. These are typically done in drawings. However, we've seen them in many different ways. Gerber files, Excel spreadsheets, in the rare instances where somebody jotted it down on a napkin even, I've seen once before. But namely, our most common way is how it shows off here to the right, where a customer would define a rigid section, a flex section, alongside all the many different layers. Regarding materials and stack-up, our standard materials typically consist of FR4 or polyimide, which many in the industry will shorten to PI for the rigid materials. Those are our most common ones. Those are, in a manner of speaking, the bread and butter of rigid sections of rigid flex boards. Now, specialized materials can be available, but it typically starts straying from the path of easy manufacturing when you start getting into specialized materials. Regarding for flex cores and cover lathe, only polyimide is supported, which regarding the core itself, it is available in both adhesive-based cores and adhesive-less cores. Adhesive-based being where the copper is adhered to the flex with an adhesive, or adhesive-less where it is strictly copper against the polyimide core itself. Coverlay itself, however, is available in many different ways in the sense of cosmetic for color, so different applications that might require different colors, black, white, or even just our standard amber. For adhesives, the only adhesives available that we use are epoxy and acrylic. Some manufacturers will support polyimide-based adhesives, but those require specialized equipment that they might go to higher press temperatures than what we support, and typically those also come at a higher premium as well. Now, more specialized materials can be available depending on use cases, and it is something that we have helped define in the past with many of our customers, such as pressure-sensitive adhesives, or PSA for short. We've evaluated designs where we see those might be necessary, or even see where those might not be necessary. But for those adhesives, they're available in standard and assembly temperature resistant varieties depending on a use case. After that, we've got shielding films. As I said earlier in the presentation, those are for when signal integrity is a core component of a design. And then we've also got stiffeners beyond the standard polyimide and FR4, such as stainless steel and aluminum. All of these are available, but generally it helps to contact us ahead of time to let us know, and so that way we can evaluate the design and help determine if these are necessary, or even add these in if we feel they are necessary. Now, starting on flex and rigid flex stack-ups. Starting with flex PCB stack-ups, these will typically range from 1 layer all the way up to 6 layers, with 1 and 2 layer being the most common. Now, flex boards tend to remain flexible even up to 6 layers. However, this flexibility can greatly diminish as layer count goes up, both from copper thickness, dielectric thickness, and any other requirements that a design might have. So regarding bend radius when it comes to flex, this is defined as the maximum amount a board can bend, either once or multiple times, before permanent deformation occurs. Now, bend radius is typically defined by the thickness of the board and the layer count, and then further defined beyond that by static bends or dynamic bends, which can greatly differ how a board is bent and to what extent the bend radius can go. These bend radii can be defined in IPC 2223, which is our main guideline for bend radii. For static bends, we like to see for 1 to 2 layers and 8 to 10 times board thickness as the minimum bend radius. And then for 3+ layers, we like to see 12 times the board thickness or more. But generally, anything above 3 layers is on a case-by-case evaluation basis for us. So as you can see, I've got an example in here for the 3-layer design, where total thickness using 1/2 ounce copper, or using our default cores for a 3-layer, ends up being approximately 10 mils total thickness. Now, if I was to use those earlier numbers, for instance, on the 3-layer for the 12 times, this ends up meaning that we have a minimum bend radius of approximately 120 mils. So dynamic bends. Dynamic bends are bends defined as what IPC might say go up to infinite amounts of bending. Per IPC 2223, these are limited to 1 and 2 layer designs with 1 layer preferred. Their minimum bend radius is significantly higher due to that necessity for more bends. So their minimum bend radius is going to be 100 times the board thickness. So as another example, I've got a 1 layer design here with 1/2 ounce copper, once again a standard stack up for us, with a total thickness that ends up being 3.6 mils. This means that even with dynamic bends, the minimum bend radius ends up being 360 mils, which in contrast to the static bend earlier for a 3 layer is 3 times greater. Regarding rigid flex stack ups, these can end up ranging a large amount from 2 layers where 1 layer is flex and 1 layer is rigid, all the way up to 14 layers and even beyond that. The main limiting factor of rigid flex actually ends up going back to the flex itself, and the minimum bend radius for that flex would follow similar rules as to what I showed for flex stack ups earlier. However, rigid flex ends up coming with its own considerations. It needs that rigid flex transition zone, which is defined as the borders right there along where the flex meets the rigid. That rigid flex transition zone needs no vias within a minimum of 50 mils distance. Now, different companies may actually have different distances. However, 50 mils is, in our experience, the one we've become most comfortable with, dictating that nothing within 50 mils and we would have no issues with the design. So I've shown an attached stack up to help explain it. Now, this section is what I've defined. It's not to scale, but it's what I've defined as the rigid flex transition zone, where the flex coverlay partially pushes in to the rigid section and the prepreg is pulled back slightly and where they meet. Now this pullback, this 50 mil transition zone requirement ends up coming from this section right here where the coverlay goes into the rigid section. This is to prevent vias from going through the coverlay and coverlay adhesive, and then should they go through assembly, causing issues later on through, at best, delamination, and at worst, even worse issues such as catastrophic destruction. Moving on to specialized construction, and starting with air gaps specifically. Now, these are a specialized construction, but in my experience so far, these are the most common specialized construction. And the stack ups for an air gap is actually shown very simply, where this middle section here on the right will actually show the words air gap and typically have it blocked out. Many customers will do similar ways, but generally the best way to show an air gap is to specifically say within the stack up for that intermediary section between flex air gap. Now moving on to asymmetric constructions. So these are going into what I defined earlier with the 2-layer rigid flex. This is where there's going to be an odd layer count in the rigid or flex sections, and where things as they appear are incredibly asymmetric. So in this case, the rigid section having a greater thickness of about 100 or 10 times at least compared to the flex section. Now, this asymmetric constructions are available for both flex and rigid flex, and for rigid flex, it's available also for the flex and rigid sections. And so moving on to ZIF constructions. Now, ZIF constructions are another incredibly common construction for us. We see it in a vast majority of the designs we have pretty much ever done. And what makes this specialized specifically is the fact that it's available in a rigid flex stack up, with a rigid section going into the flex section, which then goes into a ZIF section. Now, ZIF stack ups are also available in flex, however, they're seen as less specialized and more of a standard practice for us. Now, ZIF, for any who may not know, ZIF is defined as connectors that are zero insertion force, which makes up the ZIF. They're controlled to tight tolerances. They'll have dictated trace widths, trace space, design shapes, and their thicknesses themselves are typically controlled to roughly 300 microns, with select others for specialty manufacturers being at 200 microns instead. And they're available for both flex and rigid flex designs. Now, as shown below, I've got a ZIF stack up, and what clearly defines it as a ZIF stack up, beyond the fact that it says it's a ZIF stack up, is this stiffener right here, where a polyimide stiffener is used, and then a thickness is defined going up from this layer of copper to that polyimide stiffener, which is how in all data sheets for ZIF connectors, they will dictate that thickness right there between that copper layer and that stiffener. So for specialized constructions, we've got multiple rigid section thicknesses, which ends up being probably one of the most complicated constructions shown on this. Pricing ends up being equivalent to multiple boards, since essentially you're building two rigid flex designs at this point. And because of this difficulty and the amount of time, effort, and specialized manufacturing processes that go into it, multiple rigid section thickness designs are not available with many manufacturers. And some manufacturers, even beyond having the ability to do so, may actually have additional limits in doing so. And then finally, for specialized constructions, we've got bookbinding constructions, where a bookbinding construction is similar to a standard rigid flex. However, the different flex layers within it are at different lengths, and so it is made to be able to bend specifically in one direction primarily. And that is actually what ends up making it incredibly complicated to manufacture. At this time, we are not available to manufacture it even, because it is just such a complicated process and it is so specialized. And even beyond that, it does not end up having a lot of desirability, and not many customers will come to us asking for bookbinding. So it's proven to be a both specialized and rare construction for us. And then we've got blind and buried vias. These are incredibly common with rigid flex and flex, primarily with rigid flex. And these would even be considered buried vias, even though they technically would not be buried in the cosmetic sense, but buried vias in flex sections, where it is vias that are only in flex sections. And we can even have vias that are done in rigid sections, where it's purely the rigid section of a rigid flex design. Now, main limitation on blind and buried vias is the aspect ratio, which is defined as the size of the via in relation to the depth it travels. Many times you'll find that manufacturers will dictate an aspect ratio and say that they will not be able to support anything beyond that. And a secondary limitation is the number of sequential eliminations can be limited. So we would not be able to support, for instance, vias that go in almost every layer to the next layer, if only because so many laminations can become difficult to manufacture and can end up leading to high failure rates during the manufacturing process. So we generally prefer to keep our number of sequential laminations down. Now, discussing pricing and the effects of the technology on the price. So, as expected, cheapest is the simplest, which is a one-layer flex design. From there, price really only goes up with dual access, which has not been covered in this webinar, but has been covered on other portions of our website. With dual access being equivalent roughly to a two-layer and then going up from there. Non-standard options will increase the price, and anything non-standard is defined as the white or black cover lay, shielding, multiple stiffener thicknesses, or stiffeners that are outside of our standard polyimide or FR4, higher copper weight, and in some cases, other non-standard options can occur, but typically those are our most common ones that we'll see that will increase the price. So rigid flex pricing, it's typically greater than that of a flex combined with the rigid that it would be replacing. And in essence, that sounds almost backwards that a rigid flex would be more expensive than both rigid and flex. But in essence, that's due to the manufacturing process that goes into it. Building a rigid flex is essentially building a flex and then building a rigid around the flex. So pricing usually reflects that. Pricing for rigid flex will go up. It's going up typically with things such as blind and buried vias, the coverlet colors as mentioned earlier, higher layer count, air gap constructions, and any other specialized constructions. And regarding rigid, flex, or really anything in between, the best way to decrease the price is all about board size and layer count, or even just, if available to do so, increasing lead times. So in summary, stack-ups are the best way to define requirements for a build and in a way kind of tell a story of what the board is being used for. Bin radius is both easy to define and difficult to follow, and it can be very much a balancing act of layer count and thickness to the required bin radius, and having to juggle both to both meet what the design requires alongside what price might dictate and what the actual assembly might use. And finally, the more complicated the build, the higher the price and the longer the lead time.
Thank you, Zachary. Now, while he reviews all the questions that came in, I just want to briefly mention some of the additional PCB-based products we offer here at EPIC. For over 70 years, EPIC has designed and manufactured custom-built to print electronic products, and our expertise not only lies in printed circuit boards, but in custom battery packs, overmolded and other types of cable assemblies, flexible heaters, high reliability user interfaces, and EC fans and motors. Now I will turn it on back over to Zachary to go through some of the questions that came in.
So looking at my list of questions that I've got so far and received so far, can EPIC supply a custom stack-up for my build? EPIC can actually supply a custom stack-up if you were to contact us and present your design to us. Typically, we like to review it over a call. But if we were to review a design together, we can recommend a stack-up, or if push comes to shove, if you were to submit a thickness, copper weight requirement, use case to us, we can usually get back a custom stack-up. Excuse me. And if need be, for reference, we can also submit our standard stack-ups that we can then base custom stack-ups off of and work together to suit your needs. Do do your stack-ups consider impedance? So our standard stack-ups that were shown here in this webinar alongside our typical stack-ups that we will send to customers do not consider impedance. However, that is not to say we could not consider impedance. We have many stack-ups and impedance configurations at our hands, and we have the programs to be able to calculate it out as well. So if you were to come to us with a necessity for impedance, 50 ohms, single-ended, 100 ohms differential, anything of that nature, we'd be able to support it, and we'd be able to do a stack-up for you with that impedance in mind. Is there any way to increase flexibility of a flex without decreasing layer count? So going back in my webinar, the best way to increase flexibility beyond decreasing layer count will tend towards copper weight being a primary driving factor. So if greater flexibility is needed, we'll go from 1 ounce to half ounce or half ounce to third ounce. After that, it's dielectric thicknesses. So with heavier copper weight, like 1 or even 2 ounce, will require thicker amounts of coverlay adhesive, whereas decreasing it will let us decrease the dielectrics of both the inner core and the coverlay adhesive. So generally, best way to increase flexibility is copper weight followed by dielectrics. And then you can buy a little bit of flexibility if you're to have planes and you're to convert your plane layers to crosshatch planes. However, the degree of flexibility you're buying back by doing crosshatch would not be anywhere comparable to decreasing the copper weight or by decreasing the core or coverlay. And what is the cutoff for static and dynamic bends? Now that's kind of a tricky question. IPC 2223 will typically define static bends as bends more so towards the single digit count. They'll use the terms like flex to install or things of that nature, because static bends are meant to, you bend it once, twice, maybe 4 or 5 times in total, like if you have to do maintenance on a design or things of that nature, and you're not really intending to bend it more than 10 times at most. But IPC 2223 just kind of exemplifies static and dynamic bends. It doesn't really do a cutoff. So we would have to have a discussion and review the design, especially since there's such a difference between static bends being single number amount of bends versus dynamic bends being, per IPC, functionally infinite amount of bends. All right. And I believe that's all I've got time for questions. Now, thank you for participating. Now, if you have any additional questions, we'll be sure to reach out to you and answer them in any way we can. And I just wanted to thank everybody for coming today, and I appreciate you coming out and seeing our webinar. Thank you.